Okay, well, I think you can now see the screen. What we are going to talk today is the continuous uh, part of the image enhancement, which we talked regarding that uh, last week, and then some parties remain. If you review your book, it's from Unit 2 of our book, and then uh, why we need this part is that because there are some nice concept regarding the filtering and type of the filter, which we will use in MATLAB part of our course. One more thing that I should tell you that from today, I will give you one link regarding the task number 5. And in this task number 5, I want you to jump inside the map in the sense that there are some ready-made code, ready-made project, everything is ready. You just should read the project, run the project, have the result, report it, and if there is problem in the MATLAB code, you should rectify it. And also, if you can run this task, you become familiar more with the uh, MATLAB environment and how think you should do. I think it's useful in this form. Besides, also, you can learn from this code and maybe some further application you can develop based on this code. Then we please check the group, our group. I will share the link there. The subject you should select, but you should report me the name of the project that you select, and then it should not be repeated. If any other person select that topic, you cannot one 13 student, and after midterm of our exam, we have 5 minutes, 10 minutes presentation from your side that you should online, and then oh, my audio. Okay, let me see. And then based on that, you should present the project. Let me see now the audio is better or not, and then we will talk. Just Roy, please tell me that sound is okay now. Okay. We'll continue. Thank you. If there was any problem in the lecture, just Roy inform me on WeChat. Okay, let us see what I cook for you for today. Is as I said that we will talk regarding the image enhancement for the section B, and we should try this unit today. In today's talk, we have some talk regarding the noise model, because we know that sometimes the image that we have, it's mixed with some type of unwanted data. that this unwanted data people will call it noise. Image averaging, there is a method that we will do, and then enhancement by mask processing or especially filtering, and then some type of filter we will have a splitting filter, median, like that. And the chapter 2 or unit 2 of our book become finished if we can cover this part. It may be the lecture that we use both lecture time, is that first part and second part, and be ready for the little bit long lecture. Anyway, first of all, I put two slides for you to review the image enhancement. Just please see the two figures that are bring here. One is original one. Original image is in the left side, and the enhancement means the result after image enhancement. We talked before that in image enhancement, we have two domain of spatial and frequency domain, which in this domain, or which in these two part, a special domain technique are the techniques which directly manipulate the image pixel, and frequency domain, they are the techniques which manipulate the Fourier transform or wavelet transform of image. Besides, we have two definition as the PDF or probability density function, which in that it's contain the random variable and is the function that in that in the PDF you can describe the relevant likelihood for the random variable to take a given value. And another was the CDF, which in the formula there was fx, or the function which is the describe the probability that the real value random variable x with the given probability distribution will be found at the value less than or equal x. These was the two definition that talk in the uh, previous lecture, and now we will jump to the noise model as one part of the image enhancement that we have. One of the form noise, or one of the formula that people will use for the noise, is the Gaussian noise, which is the probability density function PDF of Gaussian noise. And with formula that I give you, which is the expressional type of the function, we have the parameter of the z, which is represent the gray level, m as the mean of the average value of the z, and s as its standard deviation. Then the standard deviation squared, S2, is called the variance of the z. In this form, mathematically easily traceable in both spatial and frequency domain. You know, this is the form of the Gaussian, as it's very famous, and I know that you have the probability course, which in that they describe the uh, Gaussian form or Gaussian formula. And in this, you will see the distribution of Gaussian noise in the figure, and the parameter of the z as the gray level, mu as the mean value, and other standard deviation, which I show here. Then you will see that at the center of this is the mu, or the parameter of mu. This parameter as the mean at the center. And then we have the plus minus of the sigma, that we can see the value, and the result of this noise distribution, we'll see the top value and also something like mid of this value as shown in the figure. Rayland noise is the another noise which we call it the probability density function of PDF of Rayland's noise, with the formula that it shows as the PZ and 2 by 3 Z minus A. And again, we have some form of expressional function when Z is greater than A. And in the case that Z is less than 0, we have the 0 value. In this formula, we have the Z, which is represent again the gray value, and the mean and variance will be calculated with the below formula. Now you will see the little bit difference than the Gaussian formula, but shape is similar because you have the expressional function, but you will see that the one part is a little bit less. You will see the variance or the margin that we can have for this function is less. And again, the mean value and the standard deviation, the different values, the noise model of the Gaussian. But similarly, there are some similar shape, but not exactly similar shape in that. Nice thing is in Gaussian noise is that you will see the margin of minimum and you will see the minimum and the maximum or the peak. I mean, you have one center point in the Gaussian formula or Gaussian noise, which it has the plus minus of something. But here you just have the top, and the value will be calculated based on the formula that they give here. Uh, L range or gamma noise, which is it's also one of the famous model of the noise. It shows the probability density function of PDF of Erlang or gamma noise, as the formula shows here. Again, you will see that you have the form of or some form of the expressional function, and the Z to represent the mean value and also the variance is again we have another form of the formula. If you want to see the figure, you will see that some similarity between the Gaussian and the Gaussian noise model, but again from the left side it's going near to the y-axis, and the gray level value, mean value, and standard deviation form are little bit different. Uh, Formula has a different formula than the Gaussian form. Then expositional noise is the other form or model of the noise, which is the probability again density function of PD of expositional noise. Then now we become more near to the expositional noise, and little bit we can say that this type of the noise is near to the Erlang noise model when the parameter b is equal to b1. Something that again you should be noted here is that the mean value and the variance is as the another formula to calculating. And if we want to see the shape, that it's purely expositional function, which the z as the gray level value, mu as the mean value, and the standard deviation has one formula to calculate. If we go more for the noise modeling part, we have another form which we call it uniform noise, which in that the probability density or PDF of uniform function is something like 1 divided by b minus a. It's become a little bit simpler than the Gaussian one. Now you will see the difference is that you don't have the exponential term here. And in that, again, the mu as the mean and variance formula as the parameter of A and B and the other calculation methods. It's near to the some pulse shape, which in that you have A and B as the margin, maximum margin and minimum margin, and then you have the peak, but you don't have the center point here. Okay, and this A and B is calculated based on the formula as the B minus A rises by 2 divided by 12. Impulse or salt and pepper noise, which is very useful in especially uh, for our topic, is the other form of the noise. And something that I should tell you, sometimes when people use uh, any picture, they will try to generate the noise, especially for image processing job. They will generate the noise on the picture and then check their routine and algorithm. That is why we should know some information or have some information regarding the noise type to see that our algorithm or our method is how much it can have the good performance based on the noise or any unwanted data. Then this impulse or salt and pepper noise is the probability density function of PDF of impulse, which we call it salt and pepper. And in that, you have the three value of in the function. You have PA, PB, and 0. When Z is equal to A, you have the probability of A. When Z is B, you have probability of B. And in the other case or any other case, you have the value where Z represents the um, gray level. Now you will see that here you don't have the mean value or you don't have the variance to calculate the values. But see, the distribution is something like that. And you have the A with the PA and PB or probability B with the value of the B. Then this is the margin or this is the noise channel that you can use. Okay, now what we learn? We learned that we have some noise type or any unwanted signal, that these are the formulate one. But maybe some of you ask me that just do we have just this form noise? No, we can have mixture of this noise. We can have combination of them. We can have some percentage of them, or maybe we can have all these noise. And probably if we have all type of this noise, then detecting the shape, it's difficult, and we should do something to remove this noise from the figure, in the sense that if we want to have the proper inspection inside of our figure, we should we should somehow try to minimize this type of the noise. Something that I tell you here, there were the formulate type of the noise, means that the type of the noise which we have some information about them and we can have the formula for them. But really, the noise don't have a fixed formula, and it can be in any form. Have this concept also. For this part of the noise, I will try to give you one table which is summarize all the noise model, and you can then learn it better. Okay, that was the first part. In the second part, I'm talking regarding the image averaging. And to know this image averaging job, uh, let us first of all consider one noisy image. You know that we show our image in the form of function x and y, means that acting the x and y or any pixel location with the function, which is formed by adding one noise of x Okay. Then I can say that if I have the noisy pictures, then my main image or original image, which I can call it f x and y, is added with the eta x and y or h x and y. Okay. It means that if I can remove this term of eta from my j, x, and y, then I have the pure photo best quality image, something like that. And in the other way, it means that if noise has the zero mean and we uncorrelated, then it can be shown as the G bar or the image formatted by the averaging of the k different noisy image. I can have this formula of the uh, G bar. And here is that there is the parameter of the K, which is shows the different noisy image. And then I can have the summation of all these small noise which is added to my pixel. Suppose I have one noisy. It means that my previous pixel or my previous or my original pixel is added with some part of noise as the eta of x and y. Then if I have the summation of all these small uh, pixel with the noise, I can say that I have one fully noisy image. Then, if I want to calculate the variance of that, we can have the variance of Gn and eta with this formula, which in that, if I increase the k, it's indicate that the variability of or noise of the pixel at each location is decreases. Okay. Then something should come in your mind that we should searching for some method to increase the key. If we increase the k, then you will see that the uh, um, the value or the variance will decrease. Then from the mathematical point of view, we are searching for expected value of the G like that, and like this formula that I showed. And output after this averaging should be the original image. These are some basic of how we can do the averaging image and what we are searching for that. Averaging image, let me now give you another concept of suppose you have the 10 reading from one sensor or 10 reading, know that what is the total performance of one suppose phenomenon or one method that people use. They will take one thing goes, we want to see that how much time it will take jump from the windows. Okay. If we test it from this 10 attempt, then we can have much more real or near to real number. Okay. Uh, then may this come in your mind that, okay, same job for the image we can do. In the sense that if we can uh, take the average from 10 or so many numbers of noisy image or noisy pixel, then we can have the good image. This is the total concept of image averaging. Let us see the effect of this mathematical calculation. Even we will see this part on MATLAB, then it may be more interesting than now. Suppose the picture A, this figure is let me give the pointer. Yes, this is my original image, number A. In the B, we have the corrupted by additive some Gaussian image. Next one, I add some Gaussian noise with the zero mean and the standard deviation of 64 gray level. You see that how my image is killed. Okay. Then C to F is or the result of, and you will see that as much as I increase the K, I mean the last one you will see, the quality of image becomes better than the noise. One. This is the good example. First, this is the original one, and then purposefully in pictures, and it's much more as you can see up here. This job can see the result or sometimes many times or for the image processing algorithm and the method. Okay, the next then part that we can talk today is the image enhancement by mask process or spatial filtering. And let us continue. First of all, we talked that figure is nothing by the matrix n by n matrix, but here also we have one spatial mask which has a dimension of n by n. And what it's is used as the assumption is that the dimension often is some odd number matrix. With this matrix element, which we call it coefficient or some weight, then spatial filtering, it's some n by n matrix, which has the coefficient or weight of the n by n. And these mask, we call it spatial filters. Okay. The gray level of the pixel at center of a spatial mask is replaced by the weighted sum, which we call it R, and we can see the summation of this weightage, which is multiplied by Z1, supposed to Zi, as we saw here. And if you will see, for the I equal to 1 to 9, which is the gray level of pixel under the mask weight of Wi, the value R is called the response of the spatial mask. The response R is some linear relation for the linear spatial filters. And the response R is a nonlinear relation with the nonlinear spatial filters. Have this point in your mind. We should talk later more about is this linear or nonlinear spatial filters. Let us see. Suppose I have the image of f, x, and y, which it has the some mask coefficient of, suppose at the center it has the w, 0 and y. Then pixel section under the mask can be something like that of f of 0 and y. And then for that you can make the mask for the image like this. Now let us see how we can use this mask part. One of the filters which people will use is the smoothing filter, which is used for blurring and noise reduction. In these, blurring is used in the some pre-processing step. As maybe I don't know, we talked regarding this or no. For analyzing the image after entering that, we have some process, and because first you should do something on your image to make it ready for the algorithm that you have. And then this process, people will call it pre-processing step, which is such as removal of small details from image process prior to object extraction. Bridging of, suppose something like bridging of small gaps in the lines or curves. Uh, Noise reduction can be accomplished by blurring with the linear filters and also by some non-linear filters. Have this in your mind. And there are three types of the smoothing filter that we know as the spatial average or low pass filter. We have mean filters and we have the median filters that all of them will help us to remove the noise and enhance the figure, or in the other words, they are going to help us to increase the quality of the data from the image. Then let us first speak regarding the special averaging special averaging or low pass filter, which in that we are going to remove the sharp gray level transaction while retraining the relatively smooth area, hence producing the blurring effect. In low pass spatial filters, the gray level of the pixel at the center of spatial mask is replaced by the weighted average of pixel under the spatial mask, for example, by weighted average of its neighborhood. And hence the low pass spatial filters is, we call it neighborhood averaging. For the mask size of n by n of low pass filtering, the response of the mask or a spatial filter can be given with the formula that you will see. We have the m by n low pass filter, low pass filter, and then the accumulation of Zi as the formula shown here. Then you can see here that if I have the example of uh, 3 by 3 matrix here, and then we can have the mask by 3 by 3, or we can have the mask by 5 by 5, which any value is multiplied by one fixed or one constant one. This 1 divided by 9 is equal to 1 divided by m by n. Here, please see this formula, 1 divided by mn. Then this 1 divided by 9 will come to picture, and rest of them are the accumulation of this. Uh, of this. Okay. Then let us see the results. Suppose the original image is like that. If I use the low pass or spatial filtering blurring, you will see that the result of my photo. Maybe you feel that okay, it's not working for us because it's corrupted image quality. But wait, we will see the result later and working. Another example, you can see some low pass or spatial filtering, which I shown here as figure 1, 2, 3. In picture 1, there is the image from the Hubble Space Telescope. Next one, there is the averaging spatial mask 15 by 50. And third one is the result of threshold. You will see that in the last photo, after doing this mask, they could specify the object that they were, something like counting the number of the star. It's become more clear for the user to extract. Okay. Um, Now I think for this part is okay. I'm going to continue the rest of the filter part in the second lecture.
Okay, well,
What we talked till now, we talked regarding the noise. We talked regarding the image averaging technique. And then after that, we talked regarding the spatial mask. First of all was the low pass one, which make the picture blur. And then after this, uh, we can do some modification or picture to extract the data. The next filter that we discuss is the mean filter, which is simply smooths the local variation in an image and noise reduce as a result of blurring in this type of the filter. We have two type of mean filter. One is that arithmetic one, which is the summation of the mentioned formula with the 1 divided by uh, mn, and then the accumulation or summation of g, s, and t. Another one is the geometric mean filter, which achieves the smoothing comparable to the arithmetic mean filter, but it tends to lose the less image details in the process. Then we have two type of mean filter uh, to work on the figure. Let us see the result. Suppose in the A, we have the X-ray of one circuit, as we showed. Then in the B, we add some Gaussian noise to the figure as the second right side pictures. And then result filtering with an arithmetic mean filter by 3 by 3, and result of filtering by geometric one is shown at the D picture. Now you will see the uh, effect of this filter on the, that these are the pre-processing job. It means that after this filtering, you will start to do the next process. And in next process, maybe your aim become declared. It's something like mm, cooking or making something ready for the next section. It means that these filters are act like this. Uh, Harmonic mill filter also it has, which it doesn't well also with other type of the noise like Gaussian, and we have the contra harmonic mean filter with this formula, which in that also we can work and do the pre-processing. Let us see the effect of these two filters type of the mean filter uh, in the figure. You will see again we have the image which is corrupted by the paper noise, another type of the noise that we talk, or impulse noise. Then in the figure, we have the image which is corrupted by the salt noise, and in the C we have the filtering by 3 by 3 of the contraharmonic one, and with the next one, the value of the Q is changed. You will see that now your pictures is become more informative than previous, and it's become smooth. That is why we call it a smoothing, a special filter to all these types. Another example should be this, which is the result of selection of right sign in counter harmonic filtering. Picture A is the result of filtering, and with the size of 3 by 3 and Q by of minus 1.5, and B is result of filtering with the Q of plus 15. You see the difference, total different mean filters. Another form of the filter which we can use at the pre-processing is the median spatial filter. In that, a low passer is used for noise noise reduction, blurs, edge, and other sharp details. One alternative approach for the noise reduction, which in that we don't want to have the blurring effect on the image, is using the median spatial filter. In median filter, the gray level of pixel at the center of a spatial mask is replaced by the median of its neighborhood and by the median of gray level of pixel under the spatial mask. Median filters are very effective when the noise pattern consists of strong spike-like components and are non-linear type of the spatial filters. This type of filter are best known for the odor statics as the odor statics filter, which is type of the filter. And now you will see some uh, performance of this type of filter on the X-ray image of circuit board, which we have the salt paper noise on that. You will see in the second picture, we have the averaging spatial mask, and the third one is the median filter. You will see that this median is actually makes this figure much more better. But again, we cannot say which filter is better here because we should see what is the next step of this filter. Maybe the second one is good with averaging a spatial mask, or maybe the last one is good, which is the median filter type. Keep it in your mind that selectors and which filter is good, which filter is bad, is just depends on the next box or next application that we have. Then some concept. Let us review one concept, and then we'll continue with the spatial uh, mode. Uh, we have the concept of yes, we have directional smoothing, which is often result of blurring edge. When we make the edge of the picture blur, this smoothing will happen. To protect the edge from this blur type, directional averaging filter use, and this spatial average all calculate in several directions, as the figure here shows. Things like theta or degrees happen between the pixels or image parts, and you will see that suppose the sixth direction is chosen, that minimum, then they will set the image for us. Based on the formula, we can have some smoothing directional to avoid the blurring of the image. Uh, homographic filtering is also one type of the filter, which in that, if we think or assume the image as the function of x and y, which is represented the term of illumination and reflectance, as we talked before, I and R, it's impossible to operate this separately on frequency components of I, X, and Y and R, X, and Y. Since here, the frequency part will come to picture and Fourier transform will do the um, best rule on that. It means that we can have the ln from the both part of the formula that we have, ln of intensity as well as reflection part. Then we can take the Fourier transform as the ft of them, and then based on that we can do this type of filtering and separate them. The processing by means of filter with the response of HU and V, we can have the HU and V multiplied by ZU and V. And then we can separate the intensity multiplied by HU and V and reflectance by the part of the RU and B. Then taking Fourier transform or IFT from both sides, we can take the some EXP formula of that, which in that the I0 of x and y and R0 of x and y, which are the illumination and reflectance components of the output image. And this approach is termed as the homomorphic, homomorphic filtering. And this formula was the concept of the homomorphic filters. And if we want to know the sequence of working of this filtering, which is used to achieve the construct, stretching, and dynamic range comparison simultaneously, since the contrast of image depends on reflectance and the dynamic range on the illumination components. You will see that I have the image. We will take the ln from that or logarithm part, and then we'll take the FFT, then multiply by the function of h, u, and b, and then take the inverse Fourier transform, which will come inside into the exp, and then j is the result of this formula. Let us see the image here, and then how the homomorphic filters act on our image. Okay, now till now we review the filtering part, and then with this, the unit 2 from our chapter is finished. We finished the main concept that I wanted to tell you today. But let us talk regarding the task that I want you do that. Let me say to Roy to stop the recording the lecture. For this part, I will try to give you some